Here are three questions from the recent exam that you took. I think it's the quiz, one of these, and students found it difficult. So I'm going to go over these questions one by one. Here's the first one. In the first one, you have a 4.6 meter rod. It's a massless rod there, and it's pinned to a frictionless pivot at O, and an 8.7 kilogram ball is attached to the other end. The ball is held at A, where the rod makes a 30 degrees angle with the horizontal. You can see the 30-degree angle there. And then it's released. So the ball is right here. It's released from there, and it swings down, either the rod and the ball. It swings down. And you have to find the tension in the rod when the ball passes through the lowest point at D. So find the tension in the rod when the ball is passing through the lowest point at D. All right, let's do this. At the lowest point, so when the ball is here, when you draw the free body diagram, you have two forces acting. One is the tension acting up through the rod, and the other is the weight of the object. So that's what is shown here, the tension acting up and the weight acting down. And since this is moving in a circular path, the net force must be equal to the centripetal force. So the net force now is going to be T minus mg, because T is up and positive, mg is down, negative, and that should be equal to the centripetal force, and that's positive because the centripetal force acts towards the center of the circle, which in this case is up, which makes it positive. So when you rearrange that, you get T as mv squared by r plus mg. So to find the tension, it's very clear that you have to find the velocity, because you have everything else. The mass is given. The radius is, of course, the length of the rod. The value of g. So we need to look for the velocity. And to find the velocity at B, we have to use the concepts of energy. Energy conservation in particular. Because when the ball is at rest here, it has potential energy. But when you let it go, all that potential energy is going to change to kinetic energy at the point D. So if you take your ground to be passing through D, then we can say that all the potential energy at A is transformed to kinetic energy at D. So here's the diagram. And to find the potential energy, you need to find the height. You need to find the total height, which is what I've drawn now. So you can see that AB is the height. And in order to find AB, first you need to find this height, which you can get from this right angle triangle, and then add it to the radius. So that's what we're going to do. And get this height. I just named it H. We're saying that potential energy at A is equal to the kinetic energy at D. So mgh is equal to 1/2 times mass times velocity squared. The masses cancel out. You have v squared is 2gh. So if we get the height, we are going to get the velocity. And the height is AC plus CB or CD, which is actually it's not CD, it's CB. So it's AC plus CB. And AC from this right triangle is 4.6 sine 30. Why? Because this is the hypotenuse and this becomes the opposite side, so it's sine. So it's 4.6 sine 30 plus CB, which is 4.6. So that gives you the height at 6.9 meter. And when you put that number in, Into that formula, we'll get the velocity. After we take the square root of that number, you get the velocity as 11.63 meter per second. And once you get the velocity, plug it back into this relation to find the tension. Okay, plus mg, which is 8.7 times 9.8, and that gives 341 Newton. So that's how you do this problem. Here is the second question. A sand mover at a quarry lifts 2,000 kilograms of sand per minute, a vertical distance of 12 meters. So it's lifting the sand, and then the sand is initially at rest and is discharged at the top of the sand mover with speed 5 meters per second. At what minimum rate must power be supplied to this machine? So when you read this question, you see that there are two processes. In the first process, the sand is being lifted, which gives it potential energy. And in the second process, it's being discharged with a speed. And so it's being given kinetic energy. So if you find the potential energy and the kinetic energy and add them up, you get the total work done. And all of this is being done in 1 minute, as you can see. And so if you divide the total work done by the time in seconds, you will get the power. So let's go. So the work done in lifting it, okay, first, the work done in lifting it is mgh, because you're giving it potential energy. That is 2,000 times 9.8 times 12. Because the height is given as 12, right? So when you calculate that, you get 235,200 joules. Second, the work done in discharging it at that speed, that is giving it kinetic energy. And kinetic energy is 1/2 times mass times velocity squared. So it's the same mass, because whatever mass is being lifted up is being discharged. So it's the same mass, and the velocity is 5. It gives you 25,000 joules. So the total work done is the sum of the two. Gives 260,200 joules. And since power is total work by time, you divide that total work done by the time taken. Time has got to be in seconds. So the 1 minute is 60 seconds. That gives it's actually 4,336 watts, which is 4.34 kilowatts, approximating it there. So that's how you do that question. In this third question, you have a 1,468 kilogram car that climbs a 5-degree slope at a constant velocity of 80 kilometers per hour. Assuming that air resistance may be neglected, at what rate must the engine deliver energy to the drive wheels of the car? And express your answers in kilowatt. So a diagram here would be really good. So let's do that. That's a picture. Nice one, right? So the car is driving up that slope, that incline, 5 degrees, and you're asked to find the power, because it says at what rate must the engine deliver energy. So the rate of giving energy is the rate of doing work, which is power. So power is work over time. But work is force times distance, and distance by time is velocity. So we get a new formula. for power, which is force times velocity. Now the velocity is given here in kilometer per hour, but it's given, we can change that to meter per second. So all we need now is the force. And why is it able to drive at a constant velocity? That's because the engine is applying a force up exactly equal to the force down, which makes the net force zero. And when the net force is zero, acceleration is zero. Or in other words, when the net force is zero, the velocity is constant. So what am I saying? I'm saying that, excuse me, whatever is the downward force should be the force applied by the engine upwards. And we know the downward force is mg sine theta, don't we? Which is when you break that, the force into the weight into its components, you actually get mg vertically down, and then you break it into mg sine theta and mg cosine in the other direction, which I'm not even drawing. You don't need it in this case. So that's why you get mg sine theta as the force. So now plug that in, and you get mg sine theta times velocity, which gives you mass times g times sine of 5 degrees times the velocity. You have to change it in meter per second. That's a quick way of changing it. Multiply by 5, divide by 18. So you get the answer as 27,863 watts, and which is 27.8 kilowatts. And considering six figures, it's 28 kilowatts. And that's how you do this question. So those are the 3 questions on the reason quiz that you took, and that will be really helpful for the coming exam. Thank you.